Hello, everybody. Thank you for attending our webinar today. We have a really exciting session, as always. I'm going to give it about a minute or so because I see people are still joining, so we'll start in 2 minutes. If you need to go to the bathroom or get some water, please do so, and then hurry back because you will not want to miss this. Okay, I hope everybody's back. For anybody who just joined us, welcome to our really exciting expert webinar. Today we're going to be covering the fragility assessment of multi-span precast concrete girder bridge in the Pacific Northwest and Cascadia Subduction Zone. For anybody who is not familiar with our company, we are Midasoft, a subsidiary company of Midas IT, and we develop a total solution service for the bridge building geotechnical and mechanical engineering fields. These are some of the software that we offer. Most of you might be familiar with our Midas Civil product, and if you haven't heard yet, we have recently updated and launched a new version of this software called Civil NX. If anybody is interested in trying that out, I will be sharing the link to our trial in the chat. If anybody is familiar with this new update of GoToWebinar, these are some tools that are going to be really helpful for you. If you need to check whether your settings for audio, camera, or if for presenters, if you're sharing your screen, you will see those buttons at the bottom down here. You can also check session information at the top left, as well as who the presenter that is currently speaking. If there's any cameras active, you will see them in this section of the screen, and then you can also check the duration of the session up top. If you would like to react or raise your hand, but preferably react to anything that the presenters say today, you can do so using the hand raise icon on the bottom left. And you can submit your questions on the top right using this little button, and then just submitting your questions here, and we will get to those questions at the end of the session. If you're having any trouble throughout the session, either listening or any issues with your microphone, you can check that using the little gear button on the top right. And now I'm going to go ahead and present our first speaker. We have Dr. Monique Head. She is a tenure associate professor in the Department of Civil Engineering at the University of Delaware. She has more than 17 years of experience in higher education. She earned her bachelor's and master of civil engineering from the University of Delaware and a PhD from the Georgia Institute of Technology and Civil Structural Engineering. Dr. Head specializes in structural engineering with emphasis on structural monitoring and evaluation using advanced technologies to quantify deformations. Her publications are centered around bridge and culvert evaluations using vision-based measurements, earthquake engineering, and the impact of the earthquake's flood load and salinity effects. Next, we have Dr. Shema Obayas. I do want to give a little bit of a shout out because she just had her doctoral hooding ceremony. So congratulations, Dr. Obias. Um, she is a research assistant in the Department of Civil Engineering and Environmental Engineering at the University of Delaware and started her PhD program at UD in 2020. She earned her bachelor's of civil engineering at the University of Al Qasidiya and Master of Civil Engineering from the University of Delaware in 2017. Her PhD research focused on the bridge analysis and earthquake engineering. Um, so, Dr. Obias, I'm going to go ahead and give you the presenter mode and you can share your screen.
Thank you so much. I hope you can see my screen now.
Yes, perfect.
Thank you. Thank you for this introduction, and good afternoon for all the attendees, and thank you for joining us today. So actually, we do have a lot to cover today, so I will start right away with the presentation. Today talks will be on vulnerability assessment of existing bridges in high seismic region, such as Pacific Northwest, which is within Cascadia Subduction Zone, where this Cascadia Subduction Zone categorized by producing large duration earthquake. So we are mainly focused on the effect of the long duration earthquake on existing multi-span precast concrete girder bridge. Let's start with a quick overview of what we will be covering today. So first we will look at the background and motivation, which will include a brief introduction to the location of the Pacific Northwest, historic ground motion, the effect of outdated seismic design standard, and also will give a brief explanation about the uniform hazard and risk target approach and how we can use the new risk target approach to evaluate the collapse of risk for existing bridges. Also, we'll move then to the ground motion selection and then the case study. So we develop a multi-span precast concrete girder bridges using an open seas model. So we'll evaluate the possibility of the flexural and shear failure for the bridges for the bridge columns. After that, we will go over the results, which will include both fragility analysis and risk target approaches. And then we'll end with the conclusion and then a Q&A. Okay, starting with the background. In this research, we focus on existing bridges in Pacific Northwest region, which include both Washington and Oregon state, where the Cascadia Subduction Zone located at the edge of these two states. Cascadia Subduction Zone is one of the biggest subduction zone around the world, and it's about 600 miles. It's run from the British Columbia up to the northern California. So the orange line in the figure here is shows the edge of the subduction zone where the subduction starts descent beneath the Pacific Northwest American plate. And then the hatch area, the orange hatch area here is the interface between the North American and subducting plate, where the great earthquake can be produced. And this characterized by its long duration earthquake and it's posing risk to the existing bridges in this area. Okay, since we are focused on the existing bridges, so let me just go over the bridge inventory in Pacific Northwest there. There are about 9,600 bridges located in in this region, and the pie chart here is shows the year of construction of the bridges, and almost half of these bridges built before 1970s, where the seismic design specification were not robust enough. And then the bridge built and designed based on codes written without the information available now on safety. And then according to AASHTO, all the bridges built before 1990s outside California considered to be conventionally designed and not seismically designed. So now we are talking about like three-fourths of the bridges that are conventionally designed and not seismically designed, where these types of bridges are not able to fully withstand the large seismic events. So looking to the bridge classes in the Pacific Northwest, the bar chart here shows the number of bridges in this region based on the main span design, and about 30% of these bridges are multi-beam or girder, and 70% of these bridges built utilizing concrete, and almost 60% of these bridges are in fair to poor condition. So the main focus of this research will be on the multi-girder bridges that are built before 1990s. Also, the slab bridges constitute a large percentage of the bridges in this region. So we evaluated the behavior of the slab bridge, but I did not include it here for this session. However, feel free to send me any email if you are interested to learn more about the slab bridges. Also, we consider the effect of skewness of the present of the skewness of the slab bridge. However, so as I said, in this session we will cover only the multi-span precast concrete girder bridge. So, okay, a brief introduction about the historic ground motion there. This figure shows the Cascadia Subduction Zone earthquake timeline. It shows the 40 major earthquake in Cascadia Subduction Zone since 7000 before Christ, and the last known earthquake was on January 1700, and it's about 320 years ago. And then the return interval for such earthquake is about 200 to 500 years. So so there is a high probability that the next earthquake will hit this region in the near future. And also, the aging bridges are more vulnerable to long duration earthquake, especially when the natural period matches the frequency content and the period of the earthquake, as we will see in the next slide. Also, as we just saw, there is a significant number of aging multi-span precast concrete girder bridge. So the vulnerability assessment of these type of bridges need to be identified, considering the substructure and superstructure complexity. So let me just introduce some terminologies before we dive into the details. First is the earthquake duration. So there are two types of earthquake duration, the long duration and the short duration. And there are several ways to define these types of duration, but the most recommended one is the 90% significant duration, which is the time interval for the strongest 90% of shaking. So the records with a significant duration larger than 40 seconds is considered to be a long duration earthquake. And then with the less than 40 seconds is considered to be the short duration earthquake. The frequency and period for the ground motion frequency is referred to the seismic wave generated by an earthquake, and it is the number of cycles within 1 second. So it's measured by hertz, and which means 1 hertz equal to 1 cycle per second. The period is inversely proportional to the frequency. So the high frequency ground motion is more damaging to the structure that has a small fundamental period, and vice versa. The low frequency is more damaging to the structure with the high period, such as high-rise building and sometimes of the bridges. So the long duration earthquake make each of these cases is worse. Worse. In other words, the worst case scenario or the more damaging event is when there is a longer duration earthquake has a frequency content matching the natural frequency of the structure. Okay, so moving to the motivation of this research. Uh, as I mentioned, the bridges built before 1990s designed with outdated safety code, and this is highly increased the risk of collapse in terms of the flexural or shear or the flexural shear failure. So one of the biggest problem with the oldest bridge is that the column of the bridges designed with a widely spaced transverse reinforcement that can easily lead to the shear failure, and in some cases the shear failure occur before even the yield of the longitudinal reinforcement. So the first, if you can see the first figure here is one example of the shear failure of the column. It shows the diagonal shear crack in lightly reinforcement concrete for pier. This is for the, I think, Washoe Bridge in Taichung. This is after the Chichi earthquake in China in 1999. the figure at the middle showing the flexural failure of the column, and then this figure here at the right is showing the flexural shear failure, and these both failure occur after 1971 San Fernando earthquake. These days, the reinforced concrete construction have higher transfer reinforcement ratio with a better detailing. That results in improving better behavior against the seismic load. So one of the problem associated with the Pacific Northwest is that this region is susceptible to an earthquake, especially the long duration earthquake. Also, there is a little work conducted on the probability of failure in terms of the flexural failure and shear failure. And also for the combined shear, flexural and shear failure for the multi-span precast concrete girder bridge that are located in high seismic region and subjected to long duration earthquakes, such the earthquakes that's produced by Cascadia Subduction Zone. And usually the most powerful earthquake can occur at the subduction zone region with a magnitude 8.5 to 9 and sometimes more than 9. So this is in this study, we will focus on the evaluating the behavior of the multi-span precast concrete girder bridge and evaluated the flexural failure and the shear failure for this type of bridge. Other problem associated with the vulnerability assessment and then the risk of collapse is the approach that is used for the design ground motion, which is ultimately will affect the structural response to earthquake. Actually, the ninth edition of AASHTO uses the uniform hazard for the design ground motion, and the figure here shows the uniform hazard for 8 locations across the Pacific Northwest, and one of the shortcomings of the uniform hazard is that they ignore the variation with the location, especially when we design for the large return period, such as 2,500 return period or 1,000 return period. Like for example, here this is show the design spectral acceleration for a 1,000 return period for the 4 different location, and if you can see here, almost the design spectral acceleration is the same for all of these locations. So this is one of the shortcomings. Other shortcoming is that it's designed based on one selected point, which is ignoring the uncertainties associated with the ground motion of the spectral acceleration of the design spectral acceleration. Actually, that's what motivates the researcher to move to risk target approach. The risk target approach, which is a combination between the fragility and hazard. I will detailing this in the upcoming slide. So also the risk is account for the effect of the one of the benefit of the risk target is account for the effect of the entire hazard curve instead of only focusing on the single value at the single return period. So, and also this will lead to have at the end we need from the risk target analysis we need to have a same or the equal risk across the country. So now this is for the new design spectral acceleration because we are working on the existing bridge, so we utilize this approach to compute the risk of these bridges and their real long duration data to find the risk of collapse and compare it with the risk limit of the design specification to see to what extent the long duration will pose a risk to these types of bridges in this region. Okay, so this figure here shows the comparison of the design spectral acceleration, the design spectral acceleration from the uniform hazard approach per AASHTO 2020 to the design value obtained using a multi-period design spectrum per AASHTO 23, which is mainly using the risk target approach. And this is for the 8 location. Again, this is for the 8 location across the Pacific Northwest, categorized into 2 groups, inland and coastal. So the comparison is here is for the 2 period, which is point 2 second period and one period. So the blue one, if you can see here, is the blue one is the AASHTO 22, and then the orange one is the AASHTO 21. AASHTO 21 using AASHTO 23 using the risk target approach. So if you can see here, these cities here represent the inland city, and if you can see how it's obvious that considering the variation of the variation of the spectral design, spectral acceleration, and uh, this figure here also showing the comparison of the design spectral acceleration for the both the 0.2 second and 1 second for the coastal cities. And then from that we can see that design spectral acceleration based on the risk target is higher than the design spectral acceleration based on uniform hazard. So the bridges that are designed according with the risk target approach may suffer less damage. Let me just also introduce another terminologies to make the rest of the presentation clear. So one of the terminologies that we will use is the hazard. Hazard is the response of single degree of freedom for structure to ground motion. Basically, it's the likelihood of the spectral acceleration being exceed for a certain time, like for example, 75 years or 50 years or 100 years. A fragility is a probability of experienced damage, like different damage, for example, like yielding, spalling, or collapse. When we combine a hazard and fragility, this will give us a risk. So the risk mainly is a probability of damage, like incident collapse within 5 years. So the risk target ground motion is a design motion to achieve equal risk level at across the country. Okay, moving to the methodology overview. The three parts are involved in the methodology for this research. The first part is the modeling. So I use the OpenSeas model. OpenSeas is one of an open source finite element software. The earthquake engineering community broadly use it to simulate the seismic response of the structure. Then the tool that we used, so I used an analytical fragility function. So the fragility function is one of the widespread methods used in seismic evaluation of the existing bridge. And then the third part, which is the risk assessment, so which is the risk target methodology implemented in an AASHTO Guide Specification for LRFD 23, which is the seismic bridge design. And this approach is a combination between the hazard curve and fragility curve. We will go over like more details about the calculation of the risk for the types of these bridges, or for the multi-span precast concrete girder bridge. Okay, moving to the ground motion selection. So in order to evaluate the potential effect of the ground motion on the bridges and buildings, so we are looking for the ground motion with the magnitude that are larger than 5.5 or maybe larger than 6, that with a close distance to rupture. And also because there are no enough records available for the Cascadia Subduction Zone, and also because our focus on long duration earthquake. So what we use a simulation ground motion that are developed by a group of the researcher at the University of Washington. So they developed the M9 simulation ground motion, which is generated for Pacific Northwest region. The ground motion created for 30 different rupture scenario for each location, and also they varied in hypocenter location, a slip distribution, and they have a large set of frequency content. So the frequency contents range from 0 to up to 10. And again, the low frequency when we do have frequency between 0 and 1, and then for the high frequency when we do have the frequency between 1 and 10 hertz. Okay, so a proper set or a proper set of the earthquake is really a critical step in developing a fragility curve. The record should contain a vast collection of different seismic intensities and earthquake magnitude, different distance to rupture, to better represent the hazard uncertainties. So for this study, we use 8 locations across the Pacific Northwest, and each location has 30 different rupture scenario, as I mentioned like in previous slide. So we are talking about 240 ground motion, and also based on the distance to rupture and then site characteristic, the location are these locations, the 8 locations are characterized into two groups, which is coastal and inland. And then the inland city categorized into 3 groups based on the shear wave velocity. So it categorized to deep basin, outside basin, and shallow basin. Also, we the table here just show the big ground acceleration and then the site class, which we consider these type of site class in our analysis. Okay, moving to the case study that we use for the analysis. So we use a two-span girder bridge with a band cap at the middle and 3 circular column and this bridge was modeled using an open seas. The bridge is located in Washington, so all the drawing and plans is from the Washington DOT. Okay, the figure here is show the superstructure and substructure configuration and then material properties. So we use an elastic properties for the superstructure and we use the fiber section for the substructure, which include both column and band. We use the elastic perfectly plastic gap to represent the behavior of the abutment using zero element, and also we subjected this model to the 240 ground motion. So for the boundary condition, both for the abutment and for the column base, we use a combination of the linear spring. All the parameters or all the equations that have been used to simulate the behavior of the abutment silent traction was based on the Karlsruhe 22. And this figure here just show the two models for the longitudinal transfers, for the longitudinal spring and then for the transverse spring. And also the figure here is just show the schema, the models of the interaction between the column space and the soil. So we use a horizontal spring and rotational spring. Okay, so moving to the material that we use for the case study. So we use concrete O1 for the unconfined concrete. These types of the concrete account for the compression of the concrete, but does not allow any tension. We use hysteretic material for the reinforcement. These types of the material has the ability to model the damage due to energy and ductility. We did the evaluation for the flexural assessment and then for shear assessment. For the flexural assessment, we used the concrete O4. So concrete O4 is characterized by predicting the crushing strength as a function of the crushing strength using Mander model. However, the other type of the concrete that is used for the shear assessment is which is concrete O6 is a uniaxial concrete objected with a tensile strength and nonlinear tension stiffness using Thorndenfeld curve, which is this one, and this represents the confined concrete. Okay, moving to like the results of our analysis. So when we evaluate the seismic damageability of the bridge, it's important to account for the directionality of the ground motion. So the Girder Bridge are analyzes the Girder Bridge here are analyzes under the set of the 2040 ground motion in longitudinal direction and in transfer direction. So the longitudinal direction produce a larger demand than the transfer direction for the girder bridge for the different components. So we calculate the displacement of the column, and then we calculate the right abutment displacement, the left abutment displacement, and the bend displacement. So for this research, we focus only on the effect of the ground motion in longitudinal direction. So, probabilistic seismic demand model. In order to predict the risk of damage to the Pacific Northwest bridges, so we have to quantify the seismic demand by this structure by developing a probabilistic seismic demand model. And then, based on that, we can define the fragility curves. The probabilistic seismic demand model is a relationship between the engineering demand parameter and then the intensity measure. So what we use here, we use a regression analysis to compute the median value of the demand, and then we use this equation to compute the dispersion of the demand. So for the flexural assessment, we use a big ground acceleration and the spectral displacement as an intensity measure. And for the shear assessment, we use a drift ratio as an intensity measure. Okay, so moving to the damage state. The damage state for the flexural assessment is based on the definition of the damage state defined by hazard. So we define four damage state, which is slight, moderate, and extensive and complete damage state, and this is the definition that are considered by hazard. And then we use a displacement ductility as an engineering demand parameter. For the shear assessment, the damage state was based on the Kolaski and Priestley, which is represented by the black line here, where this model is account for the shear force base as a function of the drift ratio and the curvature. Also, the figure here is showing the capacity of the column based on AASHTO LRFD 2020, and this is the curve line here is show the pushover analysis for this types of a bridge. So we define two damage state. The first damage state here is the peak load, and then the second damage state after the crack propagated. So moving to the fragility curve. The fragility curve describes how likely a structure will meet or exceed a specific damage state by a given ground motion. Symbolically, this is written as this equation here. And for example, the probability that the structure exceed, like for example, if we say the probability that exceed damage state 3 for given certain intensity measure, this will represent the probability of failure. Also, if we want to know the probability that this bridge will experience no damage under a certain intensity measure, this will represent the probability of that the bridge will experience no damage. There are several methods that can be used to construct fragility curve. So these some of them, so empirical method or expert based method or analytical method. This it depends on the data available. So for this research, we are using the analytical method. Again, we use a 240 ground motion, and for each ground motion, a complete analysis was performed, and then the max responses from the bridge were recorded, which is the displacement ductility in this case. The figure here is the figure here just show the probabilistic seismic demand for the bridges for the inland and coastal cities, where the intensity measure is the peak ground acceleration, and then engineering demand parameter is the displacement ductility. So for the bridge, if you can see, for the bridge, all these three columns have experienced same demand. So we just like select column number 1 for the analysis. So we recorded the data from column number 1. So as we can see here from the probabilistic seismic demand model, there is a considerable difference in the column demand for the inland cities and compared to the coastal cities, where the demand of the bridge columns is higher than in coastal cities, and that is mainly because these type of the cities are close to the active fault. So using the probabilistic seismic demand model and then the capacity limited state, the fragility curve were developed. So where the fragility curve is related the background acceleration to the probability of damage for different damage state. The probability of failure, what we can see here, again, this is for the coastal and inland city. So for the coastal, the probability of failure for coastal is higher than the probability of failure for inland, which is again is the same reason because the coastal is closer down to the active region than the inland cities. So moving to the evaluation of the National Seismic Hazard Map 2018. So the National Seismic Hazard model for the US was improved during 2017 and 2018 to include the amplification effect for long period ground motion located in deep sedimentary areas. So we compared the new National Seismic Hazard model for background acceleration with the result from the nonlinear time history analysis using M9 ground motion. So the data here was for the site class D. As we can see here from the fragility conversion, the Girder bridges will experience less probability of failure using National Seismic Hazard model, specifically for the higher background acceleration, which means that the M9 event is not well captured by the National Seismic Hazard model, and there is no obvious consideration is given to large events such as M9. Focusing on more on the effect of the deep sedimentary by itself. So since the new National Seismic Hazard Model 2018 include the effect of the deep sedimentary and also the M9 also include the effect of the deep sedimentary. So we compare the cities that are located on the deep sedimentary. So what we found that it seems that the probability of failure due to M9 is higher increase in deep sedimentary and still higher than the National Seismic Hazard model, which is still again the effect of the deep sedimentary when this area hit by M9 will be different than what the National Seismic Hazard model 2018 captured. Okay, moving to the shear assessment. So for the shear assessment, the column model in a way that ensure this column will fall in shear and not in flexural. So it was modeled with a wide space transverse reinforcement, as you can see, it's 12 inches, and we decrease the concrete strength by 30% to avoid increase the shear strength. However, also the moment of the base is also checked to be less than the moment section capacity, including the interaction effect from the axial load, just to make sure that this column will fall under shear and not under a flexural. So using so this figure here is just show the probabilistic seismic demand model. So we would use we use intensity measure as the drift ratio was an intensity measure, and then the base shear was the engineering demand parameter. So I will come back to this figure after we just present the fragility curve and then see the fragility curve, and then we will get back to this to more explain the results from the probabilistic seismic demand model. Again, using the probabilistic seismic demand model and then the capacity limit state, which I just showed the two capacity limit state, the fragility curve here were developed for the bridge. We use the drift ratio as an intensity measure. Actually, to achieve high level of safety, the proposed probability of shear failure according to ASCE should be less than 15% probability of failure. So if we can see here, we get like 0.01 based on damage state 1, and then we got 0.015 based on damage state 2. If we go back to the same figure, so all of these, the response here is higher than 15% probability of failure, and here it just represents the damage state 1, and this is damage state 1. Almost, if you can see, it's almost one third of the response is beyond damage state 2. And this is evident that the anticipated M9 may result in probability that exceed the specification, and this bridge will experience um, more damage. Okay, moving to the target collapse risk. This figure here is show the conceptual illustration of the risk calculation. So, sorry for the background. I don't know what they're doing. So this figure here is show a conceptual illustration of risk calculation, which is a combination between risk target and the fragility curves. So what we do, we calculate the risk based on M9. So if you can see the blue line here is, represent the hazard curve, and then the curve here, the dots one, it's represent the fragility curves from the M9, and then these represent the notional fragility curve. I will get to more details about the notional fragility curve. So what we did, the first, we compute the risk based on M9. Again, just a hazard curve, a combination of hazard curve and then the fragility from the M9. And then we calculate the risk based on the notional fragility. The notional fragility is a generic fragility curve adapted by the AASHTO Guide Specification to represent the failure of the column by formulation a plastic hinge. So we compare the risk. We compare the risk from the M9 to this, which is the generic one, and also we compute the risk based on USGS, which is a calibration between the load resistance factor to get the index measure that is which is based on calibrating the load and resistance factor to obtain the target reliability index, and then they use this reliability index is used to adjust the design ground motion. So we use this equation to compute the risk. So this equation is based on AASHTO Guide Specification 23, which is basically in order to compute the risk, you have to get the total probability, which is basically the multiplication, the summation of the multiplication of the numerical integration for both fragility and the hazard. Again, the specification, so based on AASHTO Guide Specification 23, what they specify the risk collapse to be 1.5 inside 5 years. And based on USGS AASHTO, the specification limit is 70% inside 5 years. In order to compute the 75 probability of collapse, we use this equation, which is 1 minus 1 minus total probability. And again, this is based on AASHTO Guide Specification for LRFD 23. So first of all, the risk based on M9. So this figure here is show the hazard curve is based on the USGS National Seismic Hazard Model. So this is for the 8 locations that are considered for the analysis. And these are just like, and also we consider for each type of hazard curve, we consider the type of the site class, which is based on shear at the upper 30 meters, the shear velocity at the upper 30 meters of the ground. So, and here is this is the risk, this is the fragility curve, and the hazard curve, which is from this chart. So since we do have like 2 groups for, so we pick the highest annual of exceedance for all the 4 cities for the inland. So Port Angeles has higher annual of exceedance, and for the coastal cities, the ocean shores has higher annual of exceedance. So these two will represent the risk for these 2 groups. For fragility curve, we use damage state 4 since we are more interested in the risk of collapse, and the damage state 4 represent the collapse. For the engineering demand parameter, we use its displacement ductility, since the displacement ductility is more represented the inelastic behavior of the bridges, which is better than the force approach, which is the acceleration time the mass. Again, the intensity measure here is the spectral displacement. So what we found that the risk target for inland to be 7.3, and then for the coastal to be 4.7. And then so the risk of collapse in inland is higher than the risk of collapse in coastal, and that's mainly because the inland cities has higher annual of exceedance than the coastal city. Again, and also these types of the risk is way higher than, or significantly higher than, the specification limit, which is 1.5, which means that these types of bridges is really under high risk of the collapse. Also, again, because we compare this to the risk target using national fragility function. So here's the figure at the middle show the national fragility. This again, this is a generic one and generic fragility function. And however, these types of the fragility represent the new design. It's not like for the existing design. And then we combine this with the annual probability of exceedance to compute the risk. So what we found that for the inland city, the risk target 2.79, which is again this risk is higher than the specification limit, which is 1.5, but still like less than what the risk is come from the existing approaches. For the coastal cities, it's still like within the specification. Actually, based on the AASHTO Guide Specification 23, in case you get like a higher risk or higher than the specification, uh, for the design ground motion, the one of the method that can be used is and increase the design spectral acceleration. And once we increase the design spectral acceleration, that will less make the fragility probability of failure less, because it's anyway the hazards is still like constant. So once we get like less probability of failure, that means we will get less risk. The third risk, and then these two, we compare them also to the USGS. So the table here is show the spectral displacement. This is based on the risk target ground motion using USGS 23. So we took these design spectral acceleration, and then we plugged it in the hazard curve, and then we compute the total probability of exceedance, and then we put this in the equation to compute the risk in 75 years. What we get, so we get for the inland cities, we get 6.5, and then for the coastal 4.25. These types of their risk is still like less than the specification based on USGS AASHTO, which is like 7% probability of exceedance. Uh, so here, just like the table here show the final conversion of the computed risk. Again, we use M9 simulated ground motion for the multi-span. Okay, so this should not be like only for the multi-span bridge. And then we use for the national fragility, which is based on AASHTO Guide specification. And so this is the limited state. And then we based on USGS AASHTO, which is 7% probability and 75 years. So we get the probability of failure for existing bridge higher than what we have for the based on the risk national and based on the USGS. Again, this is for the existing bridges, and most of these bridges that have reinforcement detail is less than what is required right now. Most of these bridges conventionally designed and not seismically designed, so we will expect that these types of bridges will have higher risk of collapse. I will move it to Dr. Head to go over the summary and conclusion and to wrap up the session.
Hey, thanks, Dr. Arbayes. Yeah, great presentation. I'll just summarize what we heard, and We're really excited about this work and what we were able to find, and report that existing multi-span pre-stressed concrete girder bridges were modeled in open seas, and we evaluated them using this vulnerability assessment framework, which is not new, but the whole point of this is that using these risk-targeted approaches, we were able to compare different methods from the AASHTO LRFD and kind of compare the pros and cons for an existing structure. A lot of this work has been mainly framed around new design, but this research really gained some insight as to some variations that need to be considered for further analysis. We also noted that both the flexure and shear failure of the multi-span precast concrete bridge columns were investigated using a fragility analysis, and that we noticed that also in the the National Hazard Seismic Maps 2018 really show the effect of the deep sedimentary basin effects, which are reflected in those maps, and moreover, its influence on how those ground motion amplifications therefore impact the structural demands. And last but not least, our collapse risk was assessed using those three different methods where the goal was to really look at risk with these different approaches. Next slide, please. And just at a high level, we're really grateful to having some of the plans that were provided for these existing bridges, where we're just highlighting some of our overall conclusions, where we noted the regional variations that you saw in those 8 locations. We were able to actually develop these fragility curves, which is really important, right? We really need those fragility curves in order to do the risk. So being able to do it for one type of bridge is great, but of course, there's going to be a need for more of those types of fragility curves for each bridge to really do this analysis. Again, we noted the effects of the deep sedimentary basin effects, which were amplified. That was shown in the coastal locations where we may see the increase of the risk, collapse risk from a megathrust earthquake. We also analyzed the shear assessment of the columns and analyzed that based on the drift ratio, where 35% of the response was more than the suggested ratio of, or suggestion of 15% probability of failure for the damage state 2 under the M9 simulated ground motion. So that does imply that there's some concerns, which is not a surprise, like Dr. Reyes said, but something we need to take into account as we think about, well, what are some of the retrofit strategies that could be used to protect these bridges, given what we might anticipate for these M9 ground motions or M9 earthquake. We noted the risk reduction and the implications for risk reduction for strategies of aging bridges, and even some more needs to probably go into that and how we really assess to account for that aging. And last but not least, as we round this out, implications. Just noting that this was just for an existing bridge, but there's really an importance to understand this more broadly in the context of establishing the seismic resilience of bridges to the seismic events without compromising functionality and safety, but really thinking about how we safeguard our structures in the future. And again, knowing that where we are for these expected motions, noting that there are some differences in the collapse risk when we're either coastal or inland, where more damage is poses a greater risk in the inland region. Next slide.
Thank you.
That wraps up our presentation for today. We've applied or provided our LinkedIn QR codes to connect with us on LinkedIn and follow our work and our email addresses. So we thank you today for your attention, and we thank Midas for allowing us the opportunity to speak with you today. So we'll now open it up for questions and answers. Thank you.
Okay, thank you guys so much. That was really great. We do have a couple of questions. I'll start with this one that asks, how long will it take to check for one bridge, for example, a 3-span bridge?
Okay, I might answer this question. So, how long in terms of the analysis, or in terms of like modeling, or in terms of what? Like, yes, the modeling is just a more challenging, always more challenging task is the developing the model. However, the risk target here is it's really a simple way using the Excel separate sheet, which is really doing a numerical integration and multiplication and then some all of these. So it won't take that much long, other than just the most important thing, the model. What it might take long just to make sure this is an accurate model, and the fragility produced or the response from this model is really represent the fragility well, and present the probability of failure well. I hope
Okay, the next, oh, go ahead.
you are good. I mean, I have this answer the
Okay,
question.
okay. The next question asks, where do most damages occur?
Okay, for this model, because if we are mainly focused on the substructure, which is on the column and band, because we are mostly focusing on the column. So absolutely, it's happened at the top and bottom of the column where the plastic formulation is that started. But because also we model the superstructure as an elastic, so we did not see any damage in the superstructure. Uh, but again, because we are just find the more damage on the column of the bridges.
Okay, and then the next one asks, how can we generate simulated ground motion?
Uh, for this question, it's because I it's already generated, and there is a lot of research, a lot of papers published on how they simulated this, because it's not me. I did not like generate the simulation. I use them from the group of the researchers, so it's available online, and then they provide a lot of information that are related to how they simulated this ground motion and how they create the model and how they consider the different scenario, and the how they include the effect of the subduction zone, and how they account for the effect of the subduction zone. So it's out of the scope of this research, but again, there is a website on the, I think, Washington, the University of Washington. If they just like said the M9 project, I think that's how they name it, they will find a lot of information how they create this model or how they create the simulation ground motion.
Okay, the next question asks, given the longitudinal displacement that were noted, is there a concern with girders falling off the beams, seats, or pier caps, or would the columns tend to fail in shears first before that might happen?
Actually, that's a really great question. This is we start to investigate this at the first time when we start to look at the different types of failure. However, we did not. I did like some work to see for the end seating, because we know based on AASHTO, the more damaging or the more collapse occur based on the end seating. However, because we are focusing on the displacement curvature ductility, so we are only work on the columns behavior. Also, since we are using the same definition of hazards, so hazards focus only on the behavior of the column, does not consider any other types. But again, these types, it should be considered like the other types of failure, such as the unseating of the abutment, the unseating of the bent cap. But for this research, we are only focusing on the behavior of the column itself.
Okay, our next question asks, in analyzing these bridges, do you consider any effects of time on the capacity of the bridges?
Um, Again, I don't get the question. So, like in terms of the time, or could you
Yeah,
repeat?
in terms of the time.
Could you
So,
repeat the question again?
yes, yes. So
Oh,
it says, in analyzing these bridges, do you consider any effects of time on the capacity of the bridges?
I got it. And no, actually, because it's the only thing that we just consider is uh, model these bridges based on what is existed there. So the bridges that we analyze is built in 1960s. So we consider all the details, all the information and reinforcement details based on the plans of these bridges and how it's built. So we did not consider any effect of the time during the life of the bridges. So we just take it as as built at the time of the bridge that is built on.
Okay, and then our next question asks, how does the fragility curve differ from doing a site-specific soil analysis to establish the spectral accelerations?
Okay, so the fragility, if we go back to the definition, the terminology, so the fragility, it's basically the probability of exceedance, like certain damage state. However, the spectral acceleration is just more represented the capacity and then the load rating of the bridge itself. So this is something related to the capacity of the structure, and this is the fragility curve. It just gives us the probability that this bridge uh, can how can exceed like certain damage state. So this is how they are different.
Okay, and then the final question we'll take today says, were you able to carry out were you able to carry out multi-load and time history analysis, and how were you able to be confident with the results?
Okay, so how I confident? This is the question. Like to be confident with the result, it just goes to the model verification. We did a lot of the verification for the model. We did like a hand calculation. We did a moment curvature analysis. We compare it with the empirical fragilities, and then we find the behavior of this bridges, and then we compare the behavior of the bridges to an actual data for the similar bridges under like an actual earthquake. So that's in if you feel if you get like a good modification, so that in this way you will feel like more confident about the your model and then your analysis. So because again we did a lot of verification which show a good agreement with with our model and then the empirical approaches, so we feel like they say just we are confident about our results.
Okay, thank you so much, Dr. Shema and Dr. Monique. I know everybody really enjoyed this session today, so thank you both for presenting it.
Thank you for, thank you so much.
Thank you
Thank
all.
you. Have a great day, everybody.